In this section, we want to talk about operations on algebraic fractions. Now, certain algebraic fractions are called rational expressions. Those are the ones that have a polynomial numerator and a polynomial denominator. And those fall into a couple of categories, proper and improper, and they kind of follow the convention of common fractions. That is, remember with common fractions, if you have a numerator that is larger than a denominator, then you have an improper fraction. Well, with rational expressions, if you have a polynomial of higher degree than the polynomial in the denominator, then you have an improper fraction as well. Well, we're not here to put problems into categories. We're here to perform operations. The operations of multiplying and dividing are fairly straightforward, and they're a little easier, I think, than adding and subtracting, because with multiplication and division, primarily you factor everything in sight, and when multiplying, you multiply numerators times numerators and denominators times denominators, and you look for cancellation opportunities in that process. Now, with division, you change the division problem into a multiplication problem. That is, you change the sign to multiplication and you flip over the second fraction. You multiply by the reciprocal. And that's all there is to it. But with addition and subtraction, common denominators come into play. And that's where a bit of manipulation opportunity presents itself. Now, if you have a common denominator, as is the case here, you just add numerators. So this is 3 plus 5 over the common denominator, 2x. So we get 8 over 2x. And once we've done that, we look for a cancellation, and we have one very simply here, 2 into 2, 1, 2 into 8, 4. So we have 4 over x. I want to make sure we understand why we can cancel, though. It's the idea that 8 is really 2 times 4, and in the denominator we have 2 times x, and we're really just taking out 2 over 2, which is a form of 1. You see, so this becomes 4 over x, and that's why. All right, when we have no common denominator, we need to identify a common denominator, then rewrite the fractions so that they both have that common denominator. The only denominator here is x, so it is the common denominator. The denominator here is understood to be 1. Now, to rewrite this fraction so that it has that common denominator of x, we multiply that factor into this denominator. But if we multiply x into this denominator, we need to also multiply x into the numerator, because we're only allowed to multiply fractions by forms of 1. If that weren't the case, we would be changing the value of the fraction. But we don't want to change its value, we want to change its form, but not its value. And so we multiply by forms of 1. All right, so when we multiply here, x times x is x squared, and in the denominator x times 1 is x. And then over here, this is plus 1 over x. Now that we have a common denominator, we can bring together the numerators. This is x squared plus 1 over the common denominator x. All right, here's one where we have a couple of binomial denominators, and they're not alike. So we have unlike denominators. The common denominator in all circumstances is some kind of expression which contains every different factor that we see in any denominator. Now, we see x plus 1 here, and we see 2x minus 1 here. The product of those two is the common denominator. I recommend that in problems like this, as they get more complicated, you deal with the greater complication through greater organization. And part of the organization in this problem is writing down the common denominator. So the common denominator is x plus 1 times 2x minus 1. Now, if you have this written down, you can refer back to it. You can look at it from time to time. And that's the value of it. All right, so when we are comparing denominators, we look at this denominator, we compare it to our common denominator, and we can notice that the factor 2x minus 1 is missing from that denominator. And in order to get it into that denominator, we multiply it in. But to multiply it in, we multiply this into both the numerator and denominator because we want to multiply by a form of 1. So that's the whole idea. So we're taking 2x minus 1 over itself and multiplying it times 1 over x plus 1. And then for this one is you compare this to the common denominator. Oh, it's missing the x plus 1 factor, so we're going to multiply the x plus 1 factor into the denominator. And therefore, we need to multiply that x plus 1 factor into the numerator as well. So we take this fraction and we multiply it by x plus 1 over x plus 1. Now, I'm going through a discussion that contains all of the important aspects of this process, because I think this is the way that you're going to want to think about these problems. And when you get confused, if you get confused, then go to a degenerate form of the situation that you have in front of you. And a degenerate form would be a problem, a similar problem involving simple fractions. And whatever you do with the simple fractions, you generally can apply the same idea here. Okay, now to help us with this multiplication process, we introduce parentheses around all of the binomials. That'll just help with the multiplication. I like that. In this numerator, we have 1 times 2x minus 1. Oh, that's 2x minus 1. In the denominator, we have the common denominator. And over here, we have 2 times x plus 1. Oh, that's 2x plus 2. And in the denominator, we have the common denominator. Now, I want you to notice that I am expanding the numerators, and I'm leaving the denominators in factored form. And there's a reason for that, and I'll tell you what it is in just a minute. Now, in the next step, we want to perform the subtraction, because here we have common denominators, so we bring together the numerators. So we're going to take this numerator and subtract that numerator. All right, so we're going to take 2x minus 1 and subtract the other numerator. And there's a great opportunity for a mistake here. And I'm going to make the mistake intentionally, and I want you to catch it. It is that you bring down this numerator and you subtract, you show that you're going to subtract that numerator. And you bring down the common denominator. I've already made the mistake. Did you catch it? The mistake is that we are subtracting this entire numerator. We are subtracting this binomial. So a minus sign preceding an understood parenthesis here means that we want to subtract 2x and we want to subtract 2. You see, so that sign has to change. That's the mistake. And it's a very commonly made mistake in algebra. And it's one that we have to look out for. Now, there are two ways to look out for it. One way is to introduce parenthesis up here and then make the sign change when you go down to this next step. Another way is to, when you write this step, you bring down the 2x minus 1, you write minus, and then you put the parenthesis around that binomial right here. And then you burn another step, changing those signs. All right, so one of those two things. But it's very important that an alarm go off when you have a subtraction problem involving a numerator that has more than one term, because this circumstance occurs in every one of those kinds of problems. All right, now the idea is to collect like terms. We collect terms in the numerator. We have 2x minus 2x. Oh, they go out. So we have negative 1 with negative 2, that's negative 3. And in the denominator, we have the common denominator, 2x minus 1 times x plus 1. Now, we can leave this in factored form, or we can multiply it out at this point. I mentioned a while ago that let's go up, our attention should go up here right now. 1 times 2x minus 1, we multiply that out. 2 times x plus 1, we multiply that out. And we multiply it out because when we get to a step down here, we're looking to collect terms, you see. We're looking for terms to go out or for terms to be collected. Whereas in the denominator, you see, we're not collecting terms. We leave the denominators in factored form because at the end of the problem, we're looking for a cancellation opportunity in some situations. Now, we don't have one here. But in some circumstances, we may have a cancellation opportunity, and we can see that opportunity if we have a factored form. We can't see it if we expand it. Now, once we know that we don't have a cancellation opportunity, we can expand this, or we can leave it in factored form. If we expand it, it becomes 2x squared plus x, let's see, 2x minus plus x minus 1. And this would be our answer. Another correct way to write the answer would be to allow this minus sign to float to a position of the sign of the fraction. Now, one thing I'd like to show you here about this, and a shortcut that can be utilized is this, that in circumstances where a couple of fractions have no factors in common, then the common denominator is going to be the product of those factors. Okay, we kind of know that from working a few problems like this. And we can utilize, it's kind of like a cross multiplication idea. It is going to be that this numerator is going to be multiplied times that denominator. See, 1 times 2x minus 1 is what we have right here. And what we have for this new numerator is 2 times the x plus 1. You see, so the shortcut way would be just to do that rather than refer to a common denominator written out to the side. Here's another one, and this one involves another nuance, and each one of these is going to involve a nuance of one kind or another. The nuance here is this, that when you look at the two denominators, you might say, oh, no common denominator, let's just kind of cross multiply using that technique that I was just telling you about. But you have to look a little more closely, and by looking more closely, you notice that the x squared minus 1 can be factored. If you have a denominator that can be factored, then you need to burn a step and go ahead and show the factored form, because it's only in looking at factors that you're able to identify a common denominator properly. Maybe I should say a least common denominator. And boy, it's pretty important to identify the least common denominator in problems like this. If you have some extra factors involved, it just makes it all the more complicated. Well, let's see. The common denominator here contains every different factor that we see. We see an x plus 1 in both of these, and we see x minus 1 in this one. So the common denominator is going to contain every one of those two different factors. The common denominator contains x plus 1, and the common denominator contains x minus 1. So this then is our common denominator, and our first fraction already has that common denominator involved in it. The second fraction needs another factor. It needs the x minus 1 factor. So we come over here and we indicate that we're going to take this fraction and multiply by x minus 1 over x minus 1. And then introducing parenthesis will help us along the way. And we have x over our common denominator. I'm going to call it CD for common denominator. Then plus 3 times x minus 1 is 3x minus 3 over the common denominator. Now that we have the common denominator in both of them, we can bring these two together. It's x plus 3x minus 3. I'm not taking any chances here by trying to make the calculations or bring together terms in this step where I'm combining the fractions. I don't want to do that because I would trip up in a problem like the one that I had before where I'm subtracting. You see, it's not too difficult here, but as the problems get more complicated, you want to be more organized, and you practice that organization with simple problems like this. All right, so this is over the common denominator. Now, x plus 3x is 4x. So it's 4x minus 3 over the common denominator, and the common denominator is that product x plus 1 times x minus 2. We can write those two factors down here. I don't see a cancellation opportunity. So we can write the factors, or we can multiply it out, and if we multiply it out, it's x squared minus 1. So that's the idea. Here's another one. Now, think about what you may need to do in this problem. Here's the problem. All right, we have a couple of denominators. They're not common denominators. In order to identify a common denominator, we need to look at factors. And in order to look at factors, we need to take out a common factor here. You see, so we're going to burn a step that will allow us to snag out this common factor of x. So I've got this 2 outside, and now I have an x factor outside of that parenthesis, and then I have x plus 2 inside the parenthesis, minus 1 over 4x. Now let's think about a common denominator. Let's write every different factor that we see. Now we need to be careful here because we're looking at the numbers, the numerical factors, 2 and 4. Now between 2 and 4, the common denominator is 4. You see, it's like this. It's like 4 can be thought of as 2 squared. If we have a factor that occurs more than once, if it has an exponent on it, then we choose that factor the most number of times that we see it in any denominator. And the most number of times we see it here is twice. Now, I said we could just look at 2 and 4 and decide that it's 4, but it's the number of like factors and the choosing of how many of them that's rather important. Sometimes those factors happen to be binomial factors, and that's where it really comes into play. But for this one, it's just 4 for the 2 and the 4. All right, I'll write the 4 out here. Now, we have an x here, we have an x there, so x is a common factor. X plus 2 appears as a factor. Doesn't appear over there, but it's part of our common denominator. So here then is our common denominator. Now we can look at this, refer to this, compare it to our denominators, and decide what factors need to be multiplied in. All right, so here we're missing, let's see, to make this 2 a 4, we need to multiply in a 2. We have the x plus 2. Oh, this is easy. We just multiply this fraction by 2 over 2. So we're doing this, 2 over 2 times this fraction. That's what we're doing. Then, now that one, let's see, we've got the 4, we've got the x, we're missing the x plus 2. Oh, that's easy. We take this fraction and we're going to multiply times, oh, I'll show it in this next step. I'll write this and show that we're going to multiply in that missing x plus 2 factor. You see, that's the idea. And now, let's see, for this one we have 2 over the common denominator, 4x times x plus 2. And in this one, 1 times x plus 2 is x plus 2. And the common denominator, 4x times, that might help, times x plus 2. And now we're bringing the two numerators together. Be careful because of this. All right, we introduce a parenthesis here and it'll help us along the way. We have 2 minus x minus 2, you see, over our common denominator, 4x times x plus 2. All right, now 2 minus 2, gee, they go out. So we have minus x over 4x times x plus 2. Oh, the x's can cancel. So if these x's cancel, we have minus nothing in the numerator. Well, not exactly nothing. We put a 1 there as a placeholder, so it's negative 1 over 4 times x plus 2. Now in problems like this, you'll often see in your book that there is a domain statement from time to time. Notice that right here, I cancel these x's. And you know, we often say that if a domain is not implied by the problem itself, that is, if we have x plus 2 in a denominator, that sort of implies that x can't take on the value negative 2. You see, so we don't write it. It's almost redundant to write x is not equal to negative 2. It's written here. The fraction is here. We know that fractions can't have denominators of 0, so it's kind of implied from the fraction. But when you cross out a factor that contains a variable, then the implication of that domain is removed from the problem. So you might see in the book here something like x is not equal to 0 as an additional idea for the domain. One idea is implied here and the other idea is written there. Anyway, that's why you see that written from time to time. The most important thing about this, though, is the overall manipulation and not so much this domain idea. Well, let's take a look at another problem. Now, this will be by far the most difficult that we have faced. And it doesn't look too tough, but just take a look at this. And I'm going to erase a little bit over here so that I'll have some room to write some stuff. Now think about what you might want to write in the next step. Think about how this might go. Now notice we're identifying a common denominator and we want to rewrite so that we have new fractions containing that common denominator. There's another nuance involved in this problem as well. This problem involves a process that in algebra it's called partial fraction decomposition, or simply partial fractions. And in algebra, that decomposition process, that partial fraction idea, leads us to a particular form that we're looking for. Now, the form that we're going to write, when we bring the three fractions together, we're going to write a particular form in the numerator, and I'll tell you right now what it's going to be. It's going to be the quadratic form. We want to have, now what's the quadratic form? Well, the general form of a quadratic is ax squared plus bx plus c. A and b are just coefficients of the x squared term and the x term. C is a constant. Now, if we write a real long item in terms of this quadratic form, then we want a coefficient of x squared. We want a coefficient of x, and we want some constant. And we specifically identify those elements. You'll see that when we get to it here. But this problem involves an awful lot of manipulation, and we need to keep track of it very carefully. Now, very quickly we see that these denominators have no factors in common, and therefore our common denominator is the product of all three. Now, if that's true, then this fraction is missing those two denominators, this fraction is missing those two denominators, that fraction is missing these two denominators, and we can just follow our nose through it and understand that. So what we're going to do is take this fraction and multiply it times x minus 3 over x minus 3 and by x plus 4 over x plus 4. So we can just go through and do that. Now I'm just going to slide way over here and start this process. So we're taking that first fraction and we're multiplying times a couple of other fractions. X minus 3 over x minus 3 and x plus 4 over x plus 4. Now, once again, it might be helpful to introduce parentheses as we go. We're going to do the same thing for the next fraction. It's b over x minus 3. And this fraction, the denominator, is missing that factor, so we're going to multiply it in. And the denominator is missing a factor from this denominator, and it's x plus 4. So we're multiplying it in, x plus 4 over x plus 4. Once again, parenthesis everywhere we see binomials. And then this fraction, plus, is missing the other two denominators, so we multiply them in. X plus 2 over x plus 2 and x minus 3 over x minus 3. Parenthesis everywhere. Now, our next task is to expand numerators. The denominators are going to sort of take care of themselves. We're not too concerned about them right now. We're looking for maybe a cancellation at the end of the problem. But it's in the numerators where all of the activity exists. Now, it's pretty easy to multiply these two, and it's more difficult to multiply by x plus 4 after we would multiply these two. So I'm going to just multiply those two and then times a. In other words, I'm going to think of it like a times x minus 3 times x plus 4. That's x squared. Middle term is minus 3x plus 4x, that's plus x. The last term, negative 3 times 4, is negative 12. So I have this. Now all of this is over the common denominator, and I'll just write it as CD for convenience. And here we have, in a similar way, I have b times, now the product of these two, x squared plus 6x plus 8, and over the common denominator. And then for this one, it is c times the product of those two, that's x squared minus x plus 6, all over the common denominator. All right. Now, let's expand further. Now, you know, when we expand these, and we have plus signs right here, once we expand in this step, we're going to put everything over the common denominator. So I'm going to anticipate that and just show the expansion of this. This is a x squared plus a x minus 12a. And then this one is plus b x squared plus 6xb. I don't know what, wait a second. I want to write this as 6 uppercase b, then x, and then plus b times 8. I'll write it as 8b, sorry. There's a convention for this, and it kind of escapes me right now. But whatever you make up for yourself, just kind of stick to it. But c times all of this, c x squared minus cx, then plus 6c. All right, all of this is over the common denominator. You see, all of this business now is over the common denominator. Now, here's what I was referring to earlier when I talked about writing this numerator in a quadratic form. We have just a whole string of terms here, and none of them are alike. We have a few of them involving a over here. These involve b, those involve c. There are no terms that are alike, so we can't bring terms together. Here's what we can do. We can notice that we have ax squared here, we have bx squared here, and we have cx squared here. So we can actually factor x squared out of all three of those terms. And when we take x squared out of those three terms, we have a plus b plus c times x squared. You see, or we have x squared times a plus b plus c. But if we're going to write this in the quadratic form, then it would be a plus b plus c x squared. You see, coefficient times x squared. You see, in the quadratic form. Now, think about that in terms of the terms involving x. Now, I've circled those. I'll underline these, double underline. Ax, I have a 6bx. And I have a minus cx. If I take x out of all of those, just imagine x coming out of all of those, and I'm going to write them as I see them. Take x out of this one, I have a. Take x out of this, I have 6b. Take x out of that one, I have minus c. I've taken x out of all of these. And then I have the constants. You see, all the rest of them represent the constant part of this quadratic form. So I'm going to write, and I'll put these in parentheses just for emphasis. I'll write minus 12a and plus 8b plus 6c. And now this, all of this, is quadratic in form. And the denominator is that common denominator, and it was that trinomial x plus 2 times x minus 3 times x plus 4. And believe it or not, this is a desirable form at some point in the study of calculus. We'll get to it in a bit. In this next problem, we have radicals involved, and we want to simplify the expression. This is a complex fraction of some sort, and we follow the rules for fractions along the way. And those rules involve common denominators and so forth. Now, you've dealt with complex fractions before, and generally we have a form which is sort of a fraction here and a fraction here, and inside this overall fraction. Now, within this problem, we have two terms up in this big numerator, and we have only one little item in this little denominator. So it's a little different than maybe we've seen before. But we go through it in the same way that we normally would. That is, you concentrate in parts of the problem. Let's concentrate up here. You see, think about this as a problem in which we're subtracting fractions. We need a common denominator. The common denominator is 2 times this radical, because this is understood to be over 1. Now, if we're changing into the common denominator, then what we need to do is multiply this into that denominator, and therefore we have to multiply this into the numerator. All right, now I'm going to speed things up here, and I want you to follow what's happening. I'm taking this, and I'm multiplying by this over itself. When I multiply 2 times the radical times this, now I better show it. The thing that I was going to go through very quickly is this, that I want you to notice that I have the square root of x plus 1 times the square root of x plus 1. When those are multiplied, you'll get the square root of x plus 1 squared. And the square root of x plus 1 squared is x plus 1. You see, so the radical sort of disappears in that little process. Now, by showing the terms like this, I'm not going to write the square root of x plus 1 squared. The squaring and the square rooting take one another out. So this part becomes, and I'm going to stay with this just through another step here, if you don't mind. I want to stay with this just one more step, and then we'll get over here. All right, this becomes, when you multiply these two, this numerator becomes 2 times x plus 1, like that, you see. And the denominator is indeed in this radical form. So it's 2 the square root of x plus 1. So that's what we get. Now over here, this fraction stays as it is. And we just bring it down into this step. And all of this is over the x plus 1. Now, where are we with the problem? We step back a little bit and we say, gee, we have common denominators up here. In these two fractions, we have common denominators, so we can bring those two together. All right, let's bring those two together. I think I'll slide back to the left. All right, so what we're doing is bringing together those numerators, and we're going to expand this as we go. So 2 times x plus 1 is 2x plus 2. And then we're subtracting the x. And all of this is over that common denominator 2 and the radical. And all of this is over the x plus 1. Now I can simplify up here, and I'd like to burn a step to do that. So we have 2x minus x is 1x. So this is x plus 2 over the radical business, 2 times the radical. And all of this is over the x plus 1. Now remember, the x plus 1 is over an understood 1 like this. So this complex fraction is really, now that we have a single fraction over a single fraction, we can think of it as x plus 2 over 2 root x plus 1 times, you see it's divided by x plus 1 over 1, but that means it's times the reciprocal of this, 1 over x plus 1. I'm assuming that you've seen this a few times before in order to be able to see this, but that's what it turns out to be. Now, when you multiply this out, you get x plus 2 times 1 is x plus 2. But think about that denominator. We have 2 times what? Well, gee, it looks like these are two different things, but they're one and the same, because this really is x plus 1 to the 1/2 power. You see, you think about the radical as a fractional exponent. So x plus 1 to the 1/2 times x plus 1. Gee, multiplying like bases, we add exponents. 1 plus 1/2 is 1 and 1/2, or 3/2. So this is 2 times x plus 1 to the 3/2 power, and this then is our answer. Sometimes when fractions are involved, it's important for us to remove a radical from either the numerator or denominator of the fraction. Now in algebra, you removed radicals from denominators. The process was called rationalization. And rationalization refers to removing a radical whether it's in the numerator or denominator. And for the purposes of our demonstrations right now, if a radical is in a denominator, we want to remove it. If it's in the numerator, we want to remove it. It'll make its appearance in the other position, but that's beside the point at this time. All right, 1 over the square root of 5. If we want to clear the radical from the denominator, here's how we think about it. We think, well, we can take the square root of a square. And so we ask ourselves, what's the smallest square that 5 goes into? Well, 5 goes into 25, and it goes 5 times. So what we're going to do is multiply this by the square root of 5 over the square root of 5. Now we're multiplying by the square root of 5 in the denominator to create a situation where we can take the square root of a square. And we're multiplying by the square root of 5 in the numerator because we can only multiply by a form of 1 in order to not change the value of the fraction. So when we do that, we get the square root of 5 in the numerator. In the denominator, we get the square root of 25. We can take the square root of 25 and it becomes 5. So this is the square root of 5 over 5, and we have rationalized this denominator. Now here's another one. Now it's commonly thought, students tend to think a lot of times, my students do anyway, that you deal with situations mathematically through memorization, and you depend upon your memory more than anything else. And I'd like to change that. I think it's more important to depend upon concepts and general ideas, because those are easier to recall than trying to memorize a whole bunch of separate information that doesn't seem to have anything to do with anything if you're just memorizing it. You see, if you understand concepts, then you can apply those concepts to an awful lot of different problems and you have much less to remember. Well, the concept here is to create a situation where you're taking the square root of a square. What students tend to do is memorize the situation like this. They tend to say, well, you always, in rationalizing, you multiply by the number that you see under the radical, always. You see, and that's what we did up here. We multiplied by the square root of 5 over the square root of 5. So you extrapolate that or extend that to the idea that we're going to multiply here by the square root of 12 over the square root of 12. Now, it's possible to get a correct answer in doing that, but it's not the most efficient way. The most efficient way is to say, what is the smallest square that 12 will go into? Because we want to create a situation where we're taking the square root of a square. So what's the smallest square that 12 goes into? And it turns out to be 36. So 12 goes into 36 3 times. So all we need to do is multiply by the square root of 3 over the square root of 3. In the numerator, we have 3, the square root of 3. In the denominator, we have the square root of 12 times 3. That's the square root of 36. We can take the square root of 36. It's 6. And now we can cancel 3 into 3, 1, 3 into 6, 2. So this turns out to be the square root of 3 over 2. Now if you multiplied by the square root of 12 over the square root of 12, you would have, well, it would be a cancellation situation. You'd have to take the square root of 12 up here and simplify and all sorts of stuff. Anyway, it's so much easier to think about it like this. All right, suppose we want to rationalize this numerator in this next problem. Well, we follow the same process that we did in rationalizing denominators. That is, we want to create a situation where we have the square root of a square. The smallest square that 7 goes into is 49, and it goes 7 times. So we're going to multiply by the square root of 7 over the square root of 7. And upstairs we have the square root of 49, and in the denominator we have 3, the square root of 7. Square root of 49 is 7, so we have 7 over 3, the square root of 7. All right, and that's all there is to it. Now, when a binomial is involved, now notice the binomial is under the single radical. That's kind of important to recognize because of what's coming up in a minute. But we still want to create that situation where we have the square root of a square. Now, to create that situation, we multiply by the square root of the x plus 1. Now, think of the x plus 1 like this. I'm just overemphasizing the situation. Because when we multiply radicands, we get x plus 1 squared, and we're taking the square root of a square in much the same way that we did up here. We just don't have to expand x plus 1 times x plus 1. You see, so we're doing this. That's what we're after. And now this is really, and I'll overemphasize it by writing this step. You see, that's what we really have in that numerator. And the square root of the square, you see, they kind of undo one another. They're inverse operations. So this is really just x plus 1. And in the denominator, we have 2, the square root of x plus 1. Okay. In this next one, in the denominator, we have a binomial. And one part of the binomial is a radical. And we'd like to rationalize that denominator. When you have a binomial like this, rather than multiply by a single square root of 2 in numerator and denominator, which wouldn't get us very far, we multiply by what's called the conjugate of the denominator. And the conjugate is a multiplication partner in which the middle term goes out, basically. But it's the same binomial with a different sign. And same binomial with a change in sign. So we're going to multiply here by 4 plus the square root of 2. And if we multiply that in the denominator, we have to also multiply it in the numerator. So it's 4 plus the square root of 2 like this. And it helps us to put parentheses around the binomials, and away we go. 3 times this business up here would be 12 plus 3 root 2. And in the denominator, now notice what happens when we multiply conjugates. 4 times 4 is 16. And just for emphasis, I want to show you the complete product here. 4 times 4 is 16. 4 times root 2 is 4 root 2. And then negative root 2 times 4 is negative 4 root 2. And then negative root 2 times root 2 is negative root 4. Now, here's the important thing about multiplying conjugates. You see, the middle term, the expected middle term of multiplying a couple of binomials. In our experience, when you multiply binomials, you get a trinomial result in many cases. And when you multiply conjugates, though, that middle term situation goes out, so you have a binomial left. And then that, in this case, is going to be able to be collected. But let's see how that happens. So all of this is over 16 minus square root of 4 is 2. So 16 minus 2, that would be 14. So 12 plus 3 root 2 over 14 is our answer. Now don't make the mistake, don't do all of this good work and then make the mistake of canceling the 12 with the 4. You see, we can't say 2 into 12 is 6 and 2 into 14 is 7. We can't do that, and because the 14 is a divisor for both parts of the numerator. You see, it's really the case that 14 divides 12 and 14 divides 3 root 2. So if we were going to make this cancellation, we would have to separate those two fractions here. And it isn't wrong to do that, but it isn't necessary either. I think this is our best answer here. Here's another one where we have a binomial involving radicals. Both of the terms of the binomial involve a radical, but once again, we multiply by the conjugate. The conjugate is the same binomial with a different sign. That's all there is to it. And so we're going to multiply here in the denominator by the square root of 5 minus the square root of 2. And if we do that in the denominator, we need to do it in the numerator as well. And away we go. Parenthesis will help us here. In the numerator, 1 times that binomial is just what we see. And in the denominator, it's particularly easy. And we're going to go through these so fast. Square root of 5 times the square root of 5 is the square root of 5 squared, or the square root of 25. The square root of 25 is 5. So we just get 5 here. And then plus times minus minus. And I'm skipping over the middle term altogether because we can anticipate that it's going to go out. So we're just multiplying the two last terms here, plus times minus minus. That's where I get this. And then root 2 times root 2 is root 4, which is 2. So 5 minus 2. So root 5 minus root 2 over 5 minus 2, 3 for our answer.